let's reconvene. Gabriel will tell us about I forgot now the title of the third lecture. You will announce it.
Yeah, no worries. Okay, good morning, everyone. So today I want to conclude some of the discussion we started last time about looking at fluctuations of output currents. So the setup that we had in mind was a master equation with some Hamiltonian and a set of jump operators. Where this K goes over some index 1, 2, 3, 4, depending on how many channels you have. And what we discussed was there's a jump unraveling. Which, I mean, in short, it can be summarized like this. At each step, you sample some probabilities, Pk to be dt average of Lk dagger Lk, and P0 as 1 minus K Pk. So these are the jump probabilities, which are tiny, proportional to dt. These are the no jump, which is the most likely outcome. And then if K is different from 0, then you update your state as by just applying the jump. And if maybe I can do it here, if K is equal to 0, then you update the state to the following smooth evolution. And I guess this part I might have used a slightly different notation last time, but it's the same thing. So if there is no jump, the evolution is smooth, rho goes into rho plus a small contribution, and this contribution is related to this non-Hermitian Hamiltonian that also encompasses the no jump information. And so by doing this, I mean, if you repeat this many times, you obtain a bit string, right? So the outcome is a bit string, something like a bunch of zeros, then every once in a while, some jump channel, and so on. Okay? So that's your data. If you were doing this experiment, this is what you would observe in the lab, right? This is the actual data. Now, of course, since 0 is the most likely outcome, an equivalent data set or data representation is to just list the channels that jumped and the times where they jumped. Right, where now here K are just the channels which are not 0, so K different from 0, and you just tell them when they jump. Each this bit string has a little delta T, right? So the time spacing here is delta T. And so you can think about it more simply as just saying the time when the jump happens and the channel that it happens, right? So this is all the information that you get if you were to do a jump unraveling in the lab. Now let me show you one example of how this applies to thermodynamics that we are currently looking at. So this is a Abbe's project. So if you want to learn more, he is the specialist in this. Suppose you have there's a canonical example of an autonomous engine, which is a 3-level maze. Of the 3-level maser. Suppose you have a single atom with 3 levels, and these 2 transitions are coupled to a hot bath, which can generate transitions like this. These 2 transitions are coupled cold bath, which can generate transitions like this. And this transition is coupled to an optical cavity, so we can emit a photon or absorb it. Right, so this is the idea of three-level laser, and the interpretation of this is an engine was given in the 1950s by Fokker and Schubois. So this is maybe the real birth of quantum thermodynamics in a sense. So let's label these transitions. Let me call space here. Let me call a jump up from the hot bath. I'll call this an injection pulse, and a jump down. I'll call this an extraction pulse. Right. So I and E label an injection or extraction of energy. And the index here labels spot. So here, for example, I'm going to have an extraction pole and an injection pole. Okay, so these are the possible transitions that the paths allow. And this one we don't know, because this is an interaction with a cavity, it's a unitary coherent thing, so we don't have access to this. Now just suppose that in the lab you can actually monitor these four transitions. I'm not saying that this is easy, but let's suppose you can. So then your string, your channel state are going to be sampled from these four symbols. Okay. So let's forget about the times for now. Every outcome has a time tag associated to it, but let's not worry about the time tag. What you would find in a typical jump sequence might be something like this. Let me just give one example of the string. Okay. Again, each one has a time tag associated with it, but we're not worrying about that right now. So this is the random kind of sequence of outcomes that you might observe. And now you can try to think, can I read out thermodynamic cycles from this? Can I, looking at this string, can I, pinpoint specific thermodynamic operations? So, for example, we can have a work extraction cycle. Which is something like this. Right? It's like a clockwise cycle. You absorb an excitation from the hot bath, you dump some energy into the cold bath, and you emit a photon. So, you go from here to here, you emit a photon into the cavity, right? And so you extracted the work. This is the work extracted is the photon that's emitted, right? We could also have this a refrigeration cycle, which will be essentially the opposite thing, right? So you are going to get some. So you absorb a photon from the cavity, and now you absorb energy from the cold bath, and you pump some energy to the hot bath, right? So now the energy flow goes this way. You use some work here, this photon, to make energy flow from cold to hot, right? And then, of course, you have the failed cycles, which are transitions where nothing really happens, right? So for this model, it's quite nice because we can play a game and we can say, just by looking at these strings, can we identify cycles, right? So here, clearly this is a failure, again a failure, but now here we see a successful cycle, where the system went, some energy was injected from the hot bath and then extracted to the cold bath, okay? And the reason why we can read this very clearly is actually related to the fact that we know exactly where the system lands after each transition in a way that we can completely keep track of where it is. So for example, suppose there is an injection hot, the system must be here. Now if there's an extraction hot, it has to be here. Then injection yeah, so the injection code, right, so if it's here, how can you have an injection code? Well, it has to absorb a photon, right, so then it kind of wiggles its way through here, and then it can inject code, so then if it's this bit, then it can eject, and so on. So you can keep track, right? This is a nice model because you can keep track of where the system is at all times. And you can identify these cycles. And this is quite interesting because now you can ask interesting questions about time resolving a thermodynamic cycle. So for example, not only can we ask what's the fraction of pairs which are successful, that's a natural question, how often we get successful work extraction, successful refrigeration, and so on. But we can also ask how long does it take to get a successful cycle? How many failures before the first success, and so on and so forth. So you can ask a bunch of statistical questions about essentially the time scale or the time resolving of thermodynamic cycles by just looking at these strengths. Yeah.
So there's the one between like the ground state and the excited state, the Smith-Lee line. How does that play into in terms of the work extraction if you have to apply a pulse or do something that brings it from this state to this state?
So I would say, I think the way I mentioned it is like this single atom is inside a cavity, right? And so whatever is happening with the cavity, you don't know. So I kind of view this as just as something that I don't know what is happening. I know that the system can go from here to here, from here to here, and I know that there is a thermodynamic interpretation for that because it has to go from here to here, has to absorb energy and so on. But whatever is happening here is the operation of the cavity. So maybe the cavity is also something later, or maybe it isn't. That part I don't know, right? All I know is that there is a kind of a specific energy consideration that I can make about this about these kind of transitions. Does that make sense?
Yeah, so we still have like a long period of time where you have nothing happens, right? Like those zeros, you still.
Yeah, exactly. So the dynamics is like this, right? So the system comes here, spends some time, random, the fact that it says here is random, and then there's a jump. So it may go back or it may go here, right? And then it spends some time here and so on. The only subtle thing is that the transitions here in this level, they are very easy to monitor because it's pretty much flat. From here, it just can go here or here. But if you're on these two levels, you have this part which you don't really know that there's a transition. For example, you can come here and then all of a sudden do this, right? And all we can keep track of is the net thing, like the time it took from go to here, right? But we can't know the time it took to go from here to here. That part we are ignorant about. This is not all nice, but it turns out that our ability to identify cycles within a bit string like this is actually not easy in general. It is possible for the simple tree-level model, and Abe has worked out other models where this can be done. But in general, it is not always easy to do it. So let me give another example. Suppose you have a string that might look like this. Sorry, where am I? Oh, sorry. Mess things up. Something like this, right? And that's all you have. I mean, the data that you get is something like this. And then you can play the game, can I identify some cycles here? This is not super easy because you see, this is clearly a cycle, right? It's good, right? But here you see that you can inject more than one excitation. There's an IH and an IH together. So you can imagine that this kind of started a cycle, right? Because you injected something from the hot bath. But then a bunch of stuff can happen before you actually, resolve your cycle in some way, before you actually get this excitation to leave to the other side. So for example, here, this would conclude here, because these are failures, nothing happened, failures, nothing happened. And this is actually a refrigeration cycle, right? It's this one where it goes like this. So in this case, in a string like this, it's actually quite difficult to identify cycles and to ask many of these nice questions about, you know, the time statistics of the cycle, because things can happen, you know, one on top of the other. Yeah.
So what does it mean that there are two IH in a row? So you have injection and then injection again, or it's stay there?
Yeah, so one example that I like to think is if you have a double quantum dot that can hold 2 electrons, right? And then you can have an IH here, suppose this gas is hot, but then you can have another one because this fits 2 electrons. Right, so then now there are 2 electrons, and then they have to start leaving at some point, but the system can hold 2 of them.
But in this case, you only have one excitation.
Yeah, so in this case, there's only one. That's the nice thing about the Gabriel. You can only have one excitation. And so this is work in progress. It's still, I mean, the conditions exactly to be able to identify cycles is still a work in progress. I just wanted to mention this because I thought it was an interesting way of, you know, I mean, this model is around since the 50s, right? We just keep coming back at it. And it's nice to view it from the perspective of time and something that is resolved into individual states and individual transition. And the number of questions that we can ask is much bigger. Because we can, you know, yeah, resolve everything in time. Yeah. Any questions? Yeah.
What would it mean to extend, like, if it's a random bit string, what would it mean to extend to, like, I don't know, large amounts of IH? We just have IH in a row, IH in a row. We keep injecting. Like, what would that look like?
Yeah, so I guess one example that might happen maybe is like if your system is like a platonic mode, which can have as many excitations as you want. Maybe it becomes less likely to have many, but in principle it can have infinity. So I think if you were to replace this with just a harmonic or an harmonic oscillator, you might run into trouble or you can get huge sequences of IH before they are unloaded.
But then I guess it being random depends on the system. So like going back to the two dot example, then you could only have 2 IHs in a row.
Yeah, but that's purely a constraint of the model, of that system,
Okay.
right? Yeah, it's like for some reason, like usually, for example, for quantum dots, they have this thing called the Coulomb blockade, which means that because electrons repel each other, because of Coulomb expression, if you put too many of them in there, it's like repel too much, so there's a tendency for a quantum dot to not accept too many electrons. So that's where this constraint that you can only have 2 electrons, that's where you physically come. Yeah.
If you have, like, there was a single atom, probably it will go through a cycle, right? So I guess you're thinking of multiple atoms, unlike, you know, on the same consciousness. One could have like these different things that can actually fail. Is that right?
I think you're right. So if I had more than one atom inside my cavity, for example, then if I'm only monitoring, depending on what I can monitor, it might be that maybe the excitation got into one atom or to another atom. Yeah. Yeah.
Are you thinking about that also in terms of other measurement things like if you have you can see there, for example, you could place it as an asymmetric thing with a double quantum dot case, and then you could have different currents in the QPC in the different charge states.
That is a very good point. So, but it's interesting that, you know, when people use QPC, so just, you know, for QPC is essentially, in this case of quantum dot, it's something that can monitor the occupation of this dot, right? So it's a continuous monitoring of how many electrons are in this dot. So then what you would get is something that this is going to go up and down, right? And this would be, I mean, you can actually extract the jump statistics from the QPC data. People have done this, right? Where they look at the data of the occupation of time and actually extract this sequence.
And I think you can do it if you place it asymmetrically, you have access to both the occupation.
Right, right. I don't know if you can say, well, I guess you probably can say to which back you can go to, because here you're assuming that you have resolution to 4 channels at least, right? Yeah.
Yeah, just when you drive it strongly, you'll split the levels again, so you'll get it more interesting. So we have two types of cycles. When there's strong driving, what happens basically get the level splitting. So if
Of this one?
of this, the ones that are coupled to the field, this one,
Okay,
and then you get more possibilities of jumps.
interesting. Let's talk about that. Yeah. Please. Any more questions?
And the master equation is solved, so you could do that.
Oh, okay. Cool. Okay, let this go. So now I want to go back a little bit to the idea of currents and show you some examples, example simulations. So recall from last time, we defined this random variable n k of t, which is the number of k clicks up to time t. Okay, so k is your channel, injection, log, whatever. You just count, right? This is a random variable. In your string, you just count how many up to this given time t. And then we can use this to build what we usually call a charge. It's going to be n of t, and it's going to be sum over k of some new k and k of t, where these new k are just physical parameters that specify the charge that you want to play with. So for example, if you want particle currents, there you might use new k to be 1 in one direction and -1 in the other direction. If you want energy current, it could be plus some energy in one direction, minus the energy in the other direction. So our physics is all contained in these new k. And the charge is an accumulated thing, like your counting stuff, and you can also define the current. I of t, which is dn dt. Okay, but one has to be a little bit careful, just because in this case, the current is a little bit ill-defined, because this variable dn it changes in discrete steps. So most of the time there are no jumps, so this is 0, and then every once in a while there's a jump, and so this is like 1 over dt, so it's like infinite. So the charge is one has to define it a little bit carefully, because we're assuming that the jump occurs instantaneously, which is of course an idealization, which means that these currents are like delta peaks. But that's not going to be a problem for us. Once we have these objects, these are really, stochastic objects, we can ask a bunch of statistical questions about it. So we can talk about the average, so the average current, the average n. But more interestingly, we can talk about the 2-point function. F of P1, P2 is the average of the current at time P1 and the current at time P2 minus the average of the current at time P1 and the current P2. So this tells you how the current is correlated at different times, how a click in one time is correlated to a click at a different time. Another thing that is useful to analyze is just the variance of the charge. So how much does the charge fluctuate? The variance of the current, kind of weird, because as I just said, it's like a bunch of delta peaks. Computing the variance of a bunch of delta peaks is kind of weird. But the variance of the charge is very reasonable. You count up to a time t, and then you see how much it fluctuates. And this, it turns out, can also be written as an integral of the 2-point function. It's just a general result. It actually doesn't. It's not restricted to quantum theory or whatever. It's just a matter of definition. So the double integral of the 2-point function. So there's a quantity which is widely used, especially in statistical mechanics, called the noise or the diffusion coefficient. Although this term, diffusion coefficient, is a slight abuse of notation because I mean, there doesn't have to be diffusion happening here, but people call it diffusion coefficient anyway, which is just the derivative of the variance. It is the rate of change of the derivative of the variance. And this has actually led to quite some confusion in recent years because some people think about this as the variance of the current, you know, because if the current is the derivative of the charge, then the derivative of the variance of the charge should be the derivative of the current, but that is not true because variances are not linear. It's going to be true for the average. I can even write that down here probably for convenience, right? So the average current is ddt of the average charge. Okay, that's true because averages are linear. But when you do it for variance, this is not true. So this has led to a lot of confusion. To be honest, this is how it started. As I mentioned, all of this is in a tutorial paper. The whole tutorial paper started because, you know, discussing with people, there was a lot of confusion about what this object meant, and you know, I started trying to kind of make sense of things. But this object called noise is not the derivative of the, not the variance of the current. We'll actually see what it is. Just by plugging this formula here for the variance, we can write this down as 2 times the integral from 0 to t dt1 f of t minus t1, where I use the fact that these are purely classical objects, so this 2-point function is symmetric with respect to the 2 time arguments. And so this noise is somehow the integral of the 2-point function. And things become much clearer if we look at steady states. So at steady state, what changes is that the 2-point function becomes a function only of the time difference. Okay. And so the noise becomes, if you think about at t going to infinity, the noise becomes 2 times the integral from 0 to infinity dt1 f of t1. And there's finally one more quantity that I want to define called the power spectrum. S of omega, which is just the Fourier transform of the 2-point function. In the steady state, so when it only has one argument on it. And so by just comparing these 2 formulas, if we look at this one and we look at this one, we see that the power spectrum is actually related to this quantity, the noise, right? So we see that the noise is just the 0 frequency component of the power spectrum. Okay. And we can compare that, so the variance of the current, I mean, if this is a 2-point function of the current, then the variance has to be just the 2-point function evaluated at time at equal times, right? So this is just f of 0, right? And so you see that indeed this noise is actually quite different from the variance of the current. Okay. So the reason why I'm mentioning all this, yeah.
So in this case, what exactly is a steady state? Random variable. So why would there be a steady state?
Sorry, that is a very good point. I meant the steady state of the master equation. So the master equation is always something like this, some superoperator times rho, and steady state is whenever this is 0. Now there's a step that I didn't show, which is that if this master equation is in the steady state, the 2-point function becomes a function only of the time difference, which is non-trivial because this is for the ensemble average, right? The master equation is for the ensemble average, and this is a quantity which is associated to the unraveling, to the random outcomes, right? So, like I mentioned before, at the level of the unraveling, there is no steady state. Things are always happening. Jumps are always happening up and down, right? So thank you for pointing that out. By steady state, I mean the steady state of the average, the ensemble average.
If you have sort of noise, because normal noise is like fluctuating dissipation is a 2-point color or fine.
Right, and this is also true here. Sorry, say again?
Normally, it's not a difference between T1 and T2. It's measurement at 2 different times. That's what noise.
I mean, the 2-point function is the correlation between 2 different times, right? But if your noise process is stationary, this only depends on the kind of distance between the 2 time points. So if you measure time 1 and 10 or 2 and 11, it doesn't.
Stationary means it does not depend on time.
Yeah, so stationary means that the thing becomes translationally invariant in time. So your noise is like, you know, if you have a noise that's just going on forever for a very long time, and so there is no, I mean, all transients are gone, and you know, things are just moving along. Then essentially the correlation. So if you have historically some current here, right? Whatever noise oscillating, if you take a point here and a point here, I mean, the correlation between this only depends on the distance. So if you move this like a window of fixed distance, the statistical correlation would be the same. Does that make sense? Any more questions? So let me give one important interpretation for this quantity D here. Suppose we have a current, right? A very long string of data, our current ITAMP, random stochastic thing, and we do a time average for a long period of time. So suppose we do, I'm going to call this I bar, and I'm going to define this as 1/t integral from 0 to big T dt I of t. This is a random module, right? Just a time average. It just, you know, average my current over time, right? We kind of expect, intuitively at least, that this is something that is essentially estimating the average current, right? Especially if a process is stationary and so on. Expect that if we average our data long enough, this should give us the average current. And indeed it does for a stationary process. And the error that we get from this, delta I bar, is for large times, d over big T. So the error that we make, if we use the time average to estimate the current, is it goes down with time. So if you take a gigantic window, the error is going to be tiny, right? But the coefficient of proportionality is exactly this noise D. So this gives a useful interpretation of what the noise means. It's associated to, you know, the precision with which you can actually estimate the average current. Yeah. Questions? Okay, so let me switch to the computer real quick. If you have any questions, let me know. Probably this time. Can everyone? So one thing that I'm not going to talk about, just, you know, for lack of time, is how to compute these quantities in practice. The important point is there are easy formulas to do this. And so this is all advertised in this tutorial paper. So if you want to compute it, there's just easy expressions to do it. The formulas might be kind of ugly or big, but the way that they're computed is very simple. So I wanted to show you 2 examples. The first example is, I think we covered this a little bit last time, is a master equation that has some Rabi oscillations, sigma x, and you can both inject or extract excitations with a thermal bath. So n bar here is the Bose-Einstein distribution of the bath that, you know, fixes the temperature. So in this case, I think I probably showed you some random trajectories, right? Where there's the Rabi oscillations in the middle, and then it can jump up and down. And here is the excitation current. So it's a current that is +1 when you get a particle, -1 when you eject it. The average current, I think we discussed this last time, is associated to the Rabi drive. So big omega is the strength of the Rabi drive. So there will be a net imbalance, right? So more current going out than coming in because you're driving your atom, right? If you're not driving, essentially you have a two-level system coupled to a bath, excitations would go in and out, but on average it would be 0. But because you're driving with the Rabi oscillations, they're not 0. And you can now compute 2-point correlation functions or power spectrum. The formulas are a little bit ugly, but they do simplify in some limiting cases. So for example, let me see if I have a plot here. I do. Let me see if it works. So is it great? Oh, no. I broke it. Wait. Let's do it like this. Oh no. There we go. It's not broken. It's just waking up. There we go. Okay, so these are the power spectra and the 2-point correlation function. And so here we have temperature. Gamma is the coupling strength to the bath. We can just set it to 1 if we want. And omega is the strength of the Rabi drive. And now what you see that is quite important is that if you have very low Rabi drive, you tend to have a power spectra that is just a one valley around 0. But as you increase the Rabi drive, this eventually splits up. So this is, if you've heard about the Mollo triplet in optics, this is associated to the Mollo triplet. If you haven't, no worries. But essentially, this is the manifestation of coherent effect, right? So these, you can actually show that when you have the power spectra and you have peaks or valleys which are not centered at 0, that this is associated to coherent oscillations and inside your system. So this is a signature of it's a signature of the coherent nature of the Rabi drive. And you see that it manifests when the Rabi drive is sufficiently strong. In the 2-point function, this appears as oscillations of the 2-point function, which is a little bit less clear than looking at the pose. And of course, you can play with temperature. Temperature will tend to make things a little bit less funny. But the oscillation still remains. So it's quite interesting that even at high temperatures, you still get these peaks, but they just become shallower and shallower. So the thermal noise just kind of washes away some of the components. Yeah.
So show the hot bath.
Sorry, in this case, it's only one bath. I forgot to say. So in this case, it's just a qubit coupled to it's just a qubit coupled to one bath, and that's it. So yeah. And then the idea is that this 2-level atom, it can gain excitations from a coherent Rabi drive, which is like shining a laser on it, or it can also gain excitations from absorbing thermal radiation, right? So these are the two processes. Yeah. If you are at 0 temperature, then you only get spontaneous emission, right? And so then you get a lot of funny or pretty looking quantum oscillations. Yeah.
This might be another question. Is there like a condition on the amplitude of coupling of the qubit to the bath? Like say like it cannot be like larger than the scale, something to the scale. Yeah, I mean the largest energy.
Right. That is a good point. So essentially, I mean, this master equation, physically speaking, it will hold for weak coupling to the bath, right? So it will hold for weak gamma. As a theoretician, we tend to not care about these things as much as we should, right? So I mean, the model is still a well-defined model for any gamma. If I put gamma equal 1 billion, it's still a valid equation, so to speak, but it doesn't mean that it will describe physically realistic processes. But you're right, physically speaking, we should probably keep this gamma low. Yeah. More questions? Yeah.
Is the power spectrum actually always symmetric? Is there situations when it's not?
So this is a very good question. It is always symmetric. The reason is because this is the power spectrum of a classical current. So this F is a 2-point correlation of classical outcome. And so F of minus T is F of T is always symmetric. And so the power spectrum will always be symmetric. You can build power spectra of, say, non-commuting currents, so to speak. and then this will not be symmetrical, but in practice, to get that in the lab, you actually have to do this kind of force vector first for different configurations, and then reconstruct the asymmetrical force vector. I mean, for these kind of classical outcomes, the force vector is always symmetrical. And so you're right that it's also a little bit silly that I'm plotting negative and positive omega, right? I'm just waiting, yeah. I'm waiting plot space, but you're right, yeah. More questions? Okay, now here's another a slightly more interesting example. So this is called a Kerr model, which can be realized in superconducting circuits, but also in any nonlinear optical system, to be honest. So the model is just a single bosonic mode, A. The Hamiltonian has some detuning delta. Now, what's called the Kerr nonlinearity is this term, A dagger, AA. So it's a nonlinear model. And I'm going to use here what's called the two-photon pump, which is essentially a process that coherently produces pairs of photons or annihilate pairs of photons. You could also do exactly the same thing that I'm doing here using a linear pump, something like A plus A dagger, it also works. And the model is also subject to some dissipation. So the basic picture of this model is that you have a cavity with some nonlinear medium inside over here, and photons can leak out of the cavity, right? So the mirrors of the cavity are like semi-transparent, so photons can leak out of it. And we describe this by the single photon loss dissipator. Now, this model is quite interesting because it has a very nice I mean, the response, of course, because this is like a nonlinear term, it can have quite a rich phase diagram, depending on how you play with the parameters. So here's one example. I'm illustrating this with the Wigner function. So this is the Wigner function of the steady state. So now coming back to your question about the steady state, here I assume that I have this cavity and just leave it on for a long time, right? And so things are still happening at the stochastic level, but at the ensemble level, nothing's happening anymore. And I just look at the steady state density matrix, and I just compute the Wigner function, right? And so the Wigner function can change shapes quite a bit. So if I change my detuning, let's say -3, it might look like a slightly squeezed state, but pretty much a thermal or a coherent state, maybe not exactly a coherent state, slightly bigger. If I keep changing this, you'll see, so I'm changing just, whatever detuning I have, this state becomes a little bit more squeezed, and eventually what is going to happen is that the state becomes so squeezed that it actually splits into two blobs. So you see now, these double blob appearing. For zero detuning, we get the two blobs nicely split. Eventually, the two blobs become completely separate, and eventually they give birth to a baby blob in the middle. Okay, it's kind of already starting to appear here. There we go. And then if you keep going, right, what is going to happen is that eventually the system becomes unstable and collapses. So maybe you can try to find something in the middle. Here you see that there are still the outer blobs, but if the detuning is too high, then it essentially vanishes. It's still, I don't know if you can see, but there's still a little there. Probably here you can see it, but that is a good point. In the steady state is always positive in this case. Yeah. So that is interesting, actually. I state like this. Sorry, let me, I guess, go for 0. But you can. The point is that this is a steady state, which ends up being a mixture of ket states. So at the level of the ensemble of the master equation, the Wigner function is always positive because you're just statistically mixing ket states. But you can actually show that this is really just a statistical mixture of two ket states. And at the level of quantum trajectories, the system will be actually jumping between ket states. So at the unraveling level, there will be a lot of entangled states, but or not entangled, but negative states. But in general, at the level of the ensemble average. Just to kind of comment on Ronnie's question. So Wigner functions can be negative, right? This one is not, it's always positive. And negative Wigner functions are usually associated to interesting quantum phenomena like cat states and so on. In this case, it's always positive because we're looking at the steady state, which is an ensemble. Okay, so this is just to say this model has been around since the 80s. It's just a fascinating model that, you know, there's so much that you can do with it. There was a revival of interest recently in using these kinds of states for quantum computation. So the argument is that, you know, if you have a state which is like a well-separated blob like this, you can call the upper blob qubit A as qubit state 0 and the lower blob qubit state 1, for example. And the reason is in superconducting circuits, you can actually realize this model quite well. And that's quite exciting. So this is just a fun, simple model. But let's look at the trajectories that we get. So here's an example of a quantum trajectory. So I'm going to focus on the triple blob setting here, and then we can change. So this is an example of a quantum trajectory. Sorry, I forgot to put labels here. Let me. Let me just put labels so this looks pretty. There we go. So what I'm plotting here on the bottom is what you would actually observe as an experimentalist, right? That's all you see. It's just clicks, right? Every time there's a vertical line, you hear a click, which is a photon count. It's a photon that leaks out of the cavity, and you hear a click. And if there's nothing, it means that there's no click. So the dynamics is just clicks and no clicks, right? If you try to reconstruct the quantum state, that's how the dynamics would look like. So that's the average number of photons inside the cavity conditioned on this data. So that's the conditional dynamics. It's like, given that I know this data, what is the best guess I can make about the number of photons inside my cavity? And what you see is that essentially the number of photons, in this particular case, the number of photons is essentially oscillating as a bright or dark source, right? So every once in a while, the cavity gets a bunch of photons and just it starts emitting a lot. So if the number of photons is high, it emits a lot. If the number of photons is low, it emits very little. And so it just keeps oscillating telegraphically, so to speak, between bright and a dark state, right? So this is quite different from the steady state. I mean, the steady state is this density matrix, is this Wegener function, right? It's just a way of visualizing the density matrix. But at the level of the quantum trajectories, you get this kind of very interesting dynamical patterns. One way to think about it is you can imagine that a system it's kind of jumping between these three states. It's like a semi-classical picture where the system is like a nonlinear oscillator that is just jumping between the triple well, like a triple well system. And the number of photons inside the cavity is related to the radius starting from the center. So if the system is in the middle blob, it will have very few photons. If the system is ever in the outer blobs, it will have a lot of photons, right? The current can't really tell if you're in the upper blob or lower blob. It can't say that, right? You just click or no click. But you can imagine that this is what is happening. And there are other measurement schemes that you can actually use to distinguish this. So, for example, you can use homodyne or heterodyne detection, which are ways that will allow you to actually tell in which blob you are, right? So it's like 3-level resolution. But if you just do photo detection, you can't really see any. And we can, and by the way, this is not only theory. So there is this very nice paper from 2018 where they actually do exactly this experiment. So this is a gallium arsenide quantum dot where they just measure the photons leaking out of it, and they see exactly this kind of pattern. So, you know, these are the actual photon counts. So it's, you know, the curve is a function of time, and they have regimes where the photon count is very slow, up to regimes which is like telegraphically, where it's up, on and off and on and on. So this is something that you can actually observe in the lab. You just put a detector in there and count photons. Let's see how this behaves at the level of the power spectrum and the 2-point function. So I'm recomputing this, but I think the plot is still perfectly valid. So what is interesting to note here, there are a couple of things that I wanted to point out. If you look at the 2-point function, you have a very clear separation of time scales. There is some oscillations here for early times, and then it's very slow decay with time. Does anyone have any guesses why this happens?
Photon loss.
Yeah, but why do you have this kind of very long tail here, where it decays very slowly with time? So this is actually related to a separation of time scale. So what the 2-point function measures is correlations in currents, right? And you see that there will be short time correlations, which is called interwell correlations, in the sense that they happen within these blocks. So a current here is correlated to a current here, right? But there will also be long range correlations about how a current here is actually correlated to something very far away. And that's what gives rise to this kind of separation of timescales. You have a short time correlation about, say, neighboring emissions, and you have this kind of long time correlation between the system flashing here or the system flashing, becoming bright here. And this is, you can actually show that this, that this is what happens. It's also associated to the distance between the blobs. So you can show that the decay of the 2-point correlation function increases with the exponentially with the distance between the blobs. So if the blobs are very far away, you get these kind of long time correlations.
That makes such a long. So this was like a noise, right? How, like, for example, correlations was like dependent on the time differences, etc.
Yeah.
I would expect not to have long time correlations, but
So the way I mean, my intuition is you can imagine you have just instead of having triple well, we can imagine a double well, right? And you can imagine that this barrier is very, very high. So what you're going to have is pretty much the dynamics within one well, which is going to live there for a long time. And then every now and then it might jump and go to the other well, right? So the short time behavior of the 2-point function tells about how currents are correlated when the system, the emitter, so to speak, is living within one well. But there are correlations between different wells as well, because whatever is happening, even though this is like rare events, right? For example, if it goes here, it's because of what's here. So there are statistical correlations between the 2 wells. And that's what's capturing the long time. That's actually the way I and in fact, this is not a restricted to quantum. If you do similar experiments for classical double well, you also get this kind of separation of time scales. And the decay of this thing is related to the separation of the wells. And now if you look at the power spectrum, what you see are 2 things. You see these kinds of valleys at non-zero frequency. Again, this is a measure of coherence, and it's associated to these coherent oscillations, right? So this is the more quantum parts, more quantum, I guess. I don't want to talk about quantum versus classical, but these are just the coherent oscillations of the oscillator. And you also see this gigantic peak here at the middle, right? So this peak at zero frequency, remember that the noise is exactly the zero frequency component of the parcel, right? So this means that the noise actually becomes very, very large, right? So the power spectrum itself is not necessarily large for all frequencies, but the zero frequency component is very large, which is again associated to these long time scales that happen. You can show that the height of this peak increases with the separation of the wells. Yeah. Yes. It holds for very weak dissipation if the dissipation term is very small. The intuition is the position of the peaks is associated to some transition energy. There's some energy difference between your system. The width of the peak is associated to the dissipation. And if it's a peak or a valley, it's associated to correlation or anti-correlation. So essentially, does an emission of an energy with some emission of a photon with some energy, is it positively correlated with a future emission or negatively correlated? That will determine if it's a peak or a valley. Yeah.
So you mentioned multi-triplets, right?
Yeah.
Can one silence and one think of these as all their times splitting?
That is a good question. I'm not sure. I mean, this would be. I think Maybe you can discuss that afterwards, because this is a slightly different current than the one used to measure model triplets. That's an emission spectrum. And this is not necessarily the emission spectrum, it's actually different. It took us a long time to understand the difference, but it is different. So maybe you can talk afterwards. I'm not sure. Yeah. Yeah.
If you have a small triplet plot, I think if you're driving, if that Rabi oscillation is, like, I think we're assuming it's on resonance with the resonant frequency, but if it's detuned, then I think you get side bands and different
Yeah.
peaks. So you can get asymmetric peaks in the sense of like the peaks, but not like the frequency peaks.
Yes. Yeah, and that's a very good point, because as I mentioned, this kind of current, oh, okay, it's gone. But this kind of current here, it's as Letitia pointed out, is always symmetric in frequency, right? So for this kind of power spectra, you never observe this asymmetry in spectra, because this power spectra is different from the emission spectra that you use to analyze the model triplet. And unfortunately, I mean, I don't have time to kind of go over the details, but you can relate the two. There are ways of relating and computing the emission spectra from this and so on. It's described in this part. Any other questions? You had a question?
Is there any particular reason why dips, they look kind of asymmetric? Since they are associated with like dissipation? I mean, they're not like kind of like, I don't know, kind of like an harmonic function. The right side is a little bit sharper than the left side.
Yeah, I think it's just, if the dissipation is very weak, you would tend to have very sharply defined peaks. And then when you mix all of them together, one peak doesn't really interfere with the other. Here, the dissipation is not so small. So I think the reason for that asymmetry is just because the central peak is kind of blurry into these side peaks a little bit. And that's why you kind of get this feel. And just a final small comment. So this is just one example. Again, I'll post this into for anyone that wants to have access to it. So this is just an example of how you might obtain the power spectra purely from the data, right? So you just get this data here. Of course, you have to do it for longer time, but you just get these pins, and then you can actually obtain the power spectrum and reconstruct it using, like signal processing, basic signal processing tools. So, it's nice that you can actually simulate what would happen in an actual experiment. Yeah. More questions? Until how long do we have? Is 12:20 or 12:30?
We have a few more minutes.
Few minutes? Okay. Then, are there any more questions? Then, if not, I'll take these minutes to actually just discuss another example, which I didn't cover the theory here at all, and apologize for that. Which is the case of diffusive measurements. So what I've shown here is this quantum jump unraveling, where there's very sharp jumps, and in between jumps nothing happens. There's another set of unravelings of the master equation, which are associated to homodyne and heterodyne detection in optics and to these quantum point contacts in quantum dots, which is a continuous measurement of a noisy current. So in this case, the basic idea is that you're constantly monitoring some observable. So I used this example here, which is a qubit, again with a sigma, with a Rabi drive, sigma x. And I'm monitoring sigma z. So I'm monitoring the occupation of the qubit. And the idea is that it's a continuous weak measurement. So I monitor it continuously, but the monitoring is also very weak. So the back action is not too bad, but also the information that I get is pretty bad, right? So there's a trade-off between how much information I get and how much back action the system has. So in this case, I mean, the definitions are quite similar. And I want to show you example for two monitoring rates. So there's this gamma here, which is the strength of my monitoring. And I'm going to show you examples for weak monitoring and strong monitoring. So this is what you get if you plot the sigma z of the qubit as a function of time, assuming that you're monitoring. Can everyone see the difference between the two curves? Maybe I can change the color. Yeah. Okay.
Black and red.
Black and red. Yeah. Yeah. So the two responses are quite different. The red one is what happens when the monitoring is very weak. So the disturbance is very small, and you can clearly see the Rabi oscillations, right? And the black one is what happens when the monitoring is very strong, and then you destroy the Rabi oscillations. This is the Zeno effect, right? So you destroy the Rabi oscillations because you're monitoring so strongly And the qubit essentially behaves classically. It just stays up for a while and then falls down and up and down and up and down, right? And so this is something that there's a kind of a transition in the sense that there's a well-defined monitoring strength, after which you completely wash away all Rabi oscillations and you just get this kind of classical behavior. And we can also analyze very similarly this. So the formulas in this example are cute. If you look at the formula for the power spectra, you see that it's essentially 1 plus a nice Lorentzian. This one here has a significance. It's called a shot noise of the measurement. So there's like a noise background, which means that even at infinite frequencies, there will be like just a level of noise in there. And this is the part associated to the Rabi oscillations. And so if we now plot this, we again see, depending on the measuring strength, you see a completely single peak, which is when there are no Rabi oscillations. And then if you make it weaker, you get again this kind of double peak. Right? And I forgot to put it here, but I will in the final version. But you can actually do exactly this kind of plot experimentally. For example, with superconducting circuits. I mean, Cater has done very, very similar experiments as well. So it's quite nice that you can actually see this kind of Zeno effect emerging from a continuous measure. Yeah.
The peaks that go up way in the black.
Yeah, right. It's like it tries to go in and fails. Yeah. So if the measurement is infinitely strong, you can view this as a completely classical stochastic process, as like a double well, where the system doesn't stay any time in the middle. So it's like this, right? It tries to go, and then either it goes or it fails. So that's why you have this kind of it goes up and tries to go and then comes back, right? So that's kind of the classical picture that you could have, that the system is trying to transition, is like it's a random model where you can, telegraph model. The system either transition or doesn't transition. But that's only true for infinitely strong monitoring. For when the monitoring is not infinitely strong, sometimes it almost transitions and doesn't, right? So it's just an artifact of having a non-infinite monitoring, so to speak. Does that make sense?
But this is always a pure state.
Oh, it's what?
This is always a pure state. It's this plot.
This is always a pure state. Sure. Yeah. If you start in a pure state, it will remain a pure state. Yeah.
And I don't see how weak monitoring can. I understand if it's a mixed state, you can go halfway, like as a statistical average, but you're measuring, you should either go halfway or.
But doesn't the red curves also go halfway?
That's because of the Rabi oscillations, right? It goes slowly.
Yeah.
But this suddenly jumps halfway. Can't be due to Rabi.
Yeah, you're right. So it's not only Rabi. The way it's going around on the block sphere is trying to Rabi oscillate, but you also have this measurement that kind of also stops it from Rabi oscillating. It's still going around block sphere. So if you see, for example, this part, it's here and then it goes up. If you plot this on the block sphere, it's actually trying to do a kind of a Rabi rotation, but it doesn't go through, right? Because it's not only Rabi oscillating, but you also have this monitoring device that is messing the Rabi oscillations. Yeah. Okay, then I guess I am done. Thank you very much. Yeah.
So that's like a strong measurement.
Yeah.
Can you also be like measurement induced executional ones, like just a really strong drive, maybe it's just kind of, I don't know, those like those kinds of plots, but I guess it could just get the measurement induced execution as opposed to like a Rabi kind of that, because it gives so many photons in that it's kind of like inducing something everybody thermal oxidation or something.
So I think in this case, it cannot be. And the reason is because I'm assuming that I'm only measuring populations, right? So you could do the same thing where you're monitoring, for example, sigma plus or sigma minus. And that would be a kind of process that might kick the qubit up or down. But if I'm only monitoring sigma z, the only thing that sigma z can do is dephase in the z basis, right? So it's just a competition between the Rabi oscillation that wants to be coherent and the dephasing in the z basis. Yeah. So in this kind of monitoring does not induce transitions. Yeah.
One of the recent research areas, measurement patients,
Yeah.
Which is basically like, separating volume law and tangled state from area law. And like in between, like there's a frequency step. So I wonder if there, like, is this some analogy, is there an analogy between this concept and what you're talking here?
Yeah, so that is a good point. This is a field that I've been kind of, seeing from a distance from a long time, wondering if I should, get my feet into it at all or not. So the way I understand it, in the beginning, people were measuring a system continuously to get these phase transitions, but they weren't really looking at the data from the measurement. They were just looking at how it affects the system. But more recently, that changed. People are now looking at, how can you infer, for example, a measurement-induced transition from the bit string data and so on. I mean, the analogy is certainly there, right? I mean, you can use this framework. There's one difference though. Some of these works, what they do is they do stroboscopic measurements. At every step delta t, you measure your system, right? And so that's kind of an active thing where you go and you measure. In a continuous measurement, you don't have this kind of setup. You're continuously measuring, and most times nothing happens, but randomly some measurement might happen. And so the description is a little bit different, and the physical implications are a bit different as well. But it's still measurement, and you get data out of it. Yeah, of course, yeah.
But your bath is still thermal.
Here, the bath is still thermal. Yes.
See the quantum conditions of which we suppress the thermal fluctuations, because otherwise,
Yeah,
you don't see any.
there actually, you don't describe your circuits, but it does actually like, bring that volume line kind of state, which is supposed to be thermal. So there's no bath indeed there.
Yeah, but the thermal fluctuations are being suppressed. That's, these experiments, it requires first reduce the thermal fluctuations. So I thought it was. But yeah, these things are interesting. Has anyone, because I think actually we have to just run these. Maybe I pose this question generally. So have people thought about quantum thermodynamics in the sense that your bath is also quantum? So it follows certain statistics, photonic statistics, fermionic statistics. Yeah. Yes. And is there any advantage in general? You can show that if there's different statistics, you get different results. What is better than the thermal, this incoherent baths that you have been.
One example that comes to mind is squeezed baths of the electromagnetic field. That's
but then in a way you're cheating because you're putting work. Yes. No, in general, I want to get something.
But isn't that true for any non-equilibrium bath as well?
You have to, if you have a heat engine, it's a hot and cold bath, that's a non-equilibrium situation. You could say, I could look at it as one bath being non-equilibrium. Food for thoughts, just first food for the body.
Food for the body.
Yes, thank you.